The remainder theorem, Algebra 2, Common Core. The remainder theorem is mostly used for us to talk about, to really test roots and factors to see if they are factors or roots on a function. And what we look for is that remainder 0 that I've been referencing, for a while now. But let me talk a little bit about this now visually. I have a graph here, and this is the graph of the polynomial function f, x cubed plus 3x squared minus 6x minus 8. If you type this into your y equals calculator, you'll see this picture. So first, is 1 a 0 of f? That's the first question that we're asking here. Is 1 a 0 of f? Now again, the term 0, there's a lot of different terms that we throw around for that 0. A 0 on a graph is an x-intercept. We often call it a root. Sometimes it's also referred to as a solution. I really like the term roots, but 0, you see that a lot. 0 and root are probably the two more common ways of talking about that, but we're all talking about the same thing. So is 1 a 0 of the function? Is it an x-intercept? So we see x-intercept of 1. Here the answer is no. So what are the x-intercepts? The x-intercepts for this graph look like we have 2, -1, -2, -3, and -4. Those are the three roots of this graph. And we can turn that into x equals -4, -1, and 2. Those are the three roots. And notice that there are three of them. The reason why there can be three of them is because our highest power is 3. This is a degree 3 polynomial, so we can have a max of 3 roots. Now, we're going to get more into this later on, that we can have less, and that would come into something called, one of the roots may have multiplicity. We could have one root with a multiplicity of 3. Or you could have one real root into imaginary roots. But we're going to get into that on another lesson. But it is helpful to know that for degree 3, you will have a maximum of 3 roots. You will never see 4 intercepts for degree 3. Then it goes from talking about roots and zeros to factors. Is x plus 4 one of the factors of f? And we have to remember how we have that connection between factors and roots. So because -4 is a root, that means that, yes, x plus 4 is a factor. So each of these roots can be written kind of going backwards as factors. Remember, the way to turn a factor, x plus 4, into a root is set it equal to 0 and solve it. -4 on both sides, -4 on both sides, you get x equals -4. So here is the factor and here is the root. We call them zeros because they have y values of 0. They're set equal to 0, and that's where they come from. So what are the zeros? We already kind of mentioned that. That's -4, -1, and 2. So what are the factors? Well, the -4 gives us a factor, or comes from a factor of x plus 4. The -1 comes from a factor of x plus 1. And the +2 comes from a factor of x minus 2. Now notice that I'm trying to put these parentheses right up against each other because they are being multiplied. Remember, when you factor something, like if I have an unrelated polynomial here, 2x minus 8, and I factor that to 2 times x minus 4. These are the two factors. 2 is a factor, and x minus 4 is a factor. And the factors multiply to 2x minus 8. Factors are the polynomial version of multiples. Like when the multiples of 10 are 2 and 5. They're multiples of 10. You can think of them as factors of 10 too. It's really the same thing. So when we're factoring and getting factors, we're getting the things that multiply to it. But not only that, the factors tell us about the roots. So these roots are connected to these factors, and these factors multiply to the polynomial. If we were to take the time here and actually multiply, these together and get a trinomial and then multiply it by x minus 2, we would get the polynomial x cubed plus 3x squared minus 6x minus 8. So the multiples of a polynomial, or the factors of a polynomial, are the x-intercepts of its graph. And so there's an important connection there. And we could easily check this. You see in my calculator, I have typed in already y equals x, the polynomial up here, and that's what this graph is. And you see it here. It's just the window's a little different than this window. That's why it's a little cut off. But if I also type into my calculator, and I already typed it in to save time, if I also type in the factors of x plus 4, x plus 1, x minus 2, and then hit graph, you'll see that it is the same graph. It's going to actually literally go right on top of it, but this time it goes in a different color because it's a color calculator. But it is the same thing, just written in a different form. And it's important to know the factored form because it's related to the roots, the zeros, the x-intercepts of that graph. And so this is just kind of graph structure in general. But where does it come into the remainder theorem? Well, the remainder theorem is really kind of more about, now, if I were to do long division with any of these as the divisor here, I would get a remainder of 0. If I were to do synthetic division with any of these divided in here, I'm going to get a remainder of 0. And not only that, if I plug any of these values in for this, like if I were to do f of negative 4, or f of negative 1, or f of 2, input that in for the x values, I will get 0. I will get 0. Because when we have an input into a function, we get the output, we get the y value. And what all of these have in common is they all have y values of 0. This is negative 4, 0. This is negative 1, 0, and 2, 0. They have y values of 0, so when we plug them in, we get 0. And when we do division, whether long division factors or synthetic division zeros, we will get 0 remainders because they have y values of 0. And when you get that 0, that means yes, it's a factor, yes, it's a root, and that's what the remainder theorem is really telling us. So if we kind of put this in almost like a definition context here, what is the connection between the remainder when polynomial f is divided by x minus a? So the value of f of a equals the remainder when the function is divided by x minus a. So f of a equals the remainder. So like over here, again, we had these three numbers that are roots. But if I were to do, like, let me find another point on this graph here. If I just go to the table, sorry, I got to get out of the pen for a second. If I were to go to the table and just find a point that's not a root, like here, 328, that looks like. 328 is a point on the graph. So if I were to do f of 3, I would get 28. So that's not a root. 3 is not a root. It has a different y value. So if x minus a is a factor, then a is a root. Probably should use a different letter than a. A is a root. If f of a equals 0, then a is a root. And not only is a root, but x minus a is a factor. Well, they're kind of saying there's a factor up here, but I want to write this down here. And x minus a is a factor. So this is all kind of saying the same thing over and over again. Remainder of 0 means it's a root. You plug it in, you get a 0. You plug it in, you get the y value. The y value is 0. That's why it is a root, because it has a 0. It's all the same thing. With the connection between, we could think of them as roots and factors, and the connection that the factors actually are what multiply to be the equation or function to begin with. So typically, the most of the problems you're going to see here is determine if this is a factor. It could also be phrased as determine if x equals negative 7 is a root or 0 of. And so really it's asking the same question, because here's the factor form, here's the root form, but they are, the same thing. We just use them different ways. So to do this, I can do synthetic division, long division. I'm going to choose to do synthetic because it's much quicker, much easier. 2, 19, 39, and 31. And we'll bring down the 2 times negative 7 is negative 14. Combine that to be 5. Multiply that to be negative 35. Combine that to be 4. Multiply that to be negative 28. And we get a remainder of 3. So is this a factor? No. And, on a test, this would probably say, explain, that type of thing. And so we would say no, the remainder is 3 not 0. I'm going to write the word there, 0. So that's really what we're talking about. You know, the other option here, I could do long division with this, I could do synthetic division with this, or I could do f of -7 and see what that comes out to be. And that would actually be, you know, substitute -7 in there, substitute -7 in there, substitute -7 in there. And again, what I would get is I would get 3. I'd get the same thing as this remainder. And that's, you know, a lot more work than I think the synthetic division, but it's helpful to know that there are a lot of different ways of writing this, a lot of different ways of doing it. But really the key here is that a remainder of 0 means that it's a factor, it's a root, it's an x-intercept. A remainder that's not 0 means that it is not. All right, so we'll talk more about this and explore the remainder theorem and the structure of graphs and polynomials later on. See ya.